in astronomy and astrophysics from UCLA in 1994 and 98. He works at JPL currently, and he's a scientist involved in numerous projects related to especially the Spitzer Space Telescope. Also, he works in education and public outreach at the JPL. His interests involve active galactic nuclei and also determination of intrinsic luminosity and their fueling mechanisms. Also infrared and radio imaging of young stars forming in various regions and their backgrounds in infrared specific spectral regions. So Dr. Gorjian is going to talk to you today about the black holes viewed from Aragats.
Thank you very much. It is very important at the beginning of each talk to take your phones out and turn them off, especially for the speaker. Thank you very much for coming. Please feel free to interrupt and ask questions, because I think fundamentally you're not going to get the most out of my talk if you're not understanding what I'm talking about. So, and if you're not asking the questions, I have no idea that you're not understanding something. So please feel free to ask questions. So I'm going to start off with just a brief history of black holes. I mean, we hear a lot about them, and we are, told very many things in TV shows and movies and so on. And I just wanted to sort of get us started on the right foot. So basically, I mean, to talk about black holes, it's to talk about gravity. And Sir Isaac Newton was the first person who gave us a good description of what gravity is. But what's interesting is that his description of gravity didn't actually include how gravity would affect light. And if you'll pardon me just for this, because I will have just this one formula. I don't like putting formulas on talks, but this is his formula for gravity. You don't have to remember it, but all you need to notice is that it has two m's in there. And the force between one mass, that's one of the m's, and the other mass is definitely, you have to put in both masses. And light actually doesn't have mass, so that's multiplying by 0. So light should not be in any way affected, according to Newtonian gravity, at all. Basically, light does not see gravity. So we'll start off there. Of course, other people kept thinking about it. In 1783, there's a guy named John Mitchell. He thought about that there might be an object massive enough to have an escape velocity greater than the speed of light, and nothing moves faster than the speed of light. And they weren't quite sure that was the case, but they certainly knew it was a very fast speed. Then in 1796, Laplace, who've taken some sort of advanced mathematics, he always did tons of advanced mathematics stuff, he actually thought about the idea of black holes, that there could be basically what he would call the largest luminous bodies, meaning that stars that were very massive in the universe may just be invisible because they would not allow light to escape. So, but nobody had any way of putting this to a formula to say anything serious about it, because Newton was the one who had the gravity description, and Newton's gravity doesn't work on light. Then we get Albert Einstein. He published his theory of general relativity, and that is about gravity. And he says, no, gravity isn't a force. Any mass bends space. And what you see, anything that falls, that curve that it falls on, that's the curvature of space. So now you don't need mass anymore. Whether light has mass or not, doesn't matter. Everything follows space. If there's a mass, space gets curved, therefore light takes a different path. So now, mass will affect the path of light, and now you can actually start doing calculations. And just barely a year after, a man named Carl Schwarzschild used Einstein's theory of general relativity to define a black hole and say, how big is this black hole? And he said, okay, well, if you have a lot of mass concentrated in a very little space, you have to take a lot of mass, just squish it, tiny, tiny little space. At what point from that, what is the distance that light can no longer escape? That would be black. And so that today is known as the Schwarzschild radius. What's interesting is Arthur Eddington who was a big relativity guy who helped prove the theory of relativity, and Einstein hated the idea of black holes. They didn't think it was possible. They were just saying you can never get matter that squished. It's just going to get, matter will resist your crushing it that on a smaller scale. And so then we get to Subrahmanyam Chandrasekhar, who basically, he said, let's follow this through. What happens if you start crushing matter? Squeezing it tighter and tighter. Well, where are we going to have that? Well, we'll have it in a star. So how does a star work? Well, a star has mass, which means the gravity is pulling in, but it's generating energy, so which generates pressure to keep the weight out. So gravity pulling in, energy being generated, pushes out, equilibrium. That's the way our sun works. That's the way every star works. Now, the Earth, of course, doesn't work like that because the Earth isn't generating energy, but the gravity, the mass is pulling everything in, but the structure of matter is resisting that. So it's providing its pressure not because it's converting hydrogen into helium or some other nuclear process, it just pushes out. So now you have this sort of equivalence between pressure and gravity, so then you have, but what happens when the pressure goes away? You have all that mass. Gravity's going to win. Gravity's going to start pulling in. But matter has an answer for that. It has a wonderful name called electron degeneracy pressure. And it has, this part of physics has some horrible, horrible names. So it's electron degeneracy pressure, and it means something very specific. But the idea is that if you pack all of the atoms in a star together to the point where every electron is packed right next to another electron and it can't move, that will exert a pressure, and it will stop the collapse. Okay, so we've done it. In fact, if you take our sun, once it runs out of fuel, the gravity will pull everything in, but electron degeneracy pressure will stop it at an object the size of the Earth. And that's called a white dwarf. But what if it's more massive than the sun? What happens then? There's something called neutron degeneracy pressure. Now, you've taken the electrons, which were all packed together and they had no place to move. If you have enough mass, you're going to squish them together some more. You're going to take the electrons, shove them into the protons, and you're going to make it into neutrons. So all you have left now are neutrons. And the neutrons are packed together and you can't squeeze them together anymore. That's called neutron degeneracy pressure. So if you took something the mass a little bit more than our sun, about 1.4 times the mass of our sun, and you took the fuel away, had gravity do what it does, that thing will squish down to something the size of Los Angeles. But what if you're even more massive than that? About 3 times the mass of the sun. Neutron degeneracy pressure cannot go against gravity. Nothing we know of can go against gravity. Gravity wins. So what you do is you take all of that mass, more than 3 times the mass of the sun, it crushes itself to the point of what's called a singularity. What's a singularity? It's a word to describe meaning we don't know. It's basically divide by 0, because you have a lot of mass and you have 0 volume. What's the density? Mass divided by 0. Oh, wait a minute. You can't do that. So all it says is we don't know. But that's what happens. That's what a black hole is. You've taken a lot of mass, let basically gravity win, crushing to the point where we don't know what happens, but we can't see what happens anymore because escape velocity is that of speed of light. So there's no light that's going to escape from it for us to see it. It's going to be black. So Chandrasekhar was a key person who did a lot of the developments on white dwarf masses, and in fact the mass at which you can become, the limit-doing mass to a white dwarf is in fact called the Chandrasekhar mass. And it wasn't until about 30 years later than that another physicist named John Wheeler coined the term black hole. Apparently a lot of people thought that was a very obscene name, but we use it as it is today. But all of this was pretty much all theory. Great, yes, neutron degeneracy pressure stops you from collapsing anymore. White dwarfs, they were starting to detect objects which were very small, had the right mass to be white dwarfs, but neutron stars were just crazy. And then Jocelyn Bell, in fact, discovered neutron stars because they tend to be very small and spin